All right, so those two questions in the last one. Let's just look at this picture. This is really what they're asking you to look at to answer the questions. All right, so let's look at this. During a time of new moon, so look, during a new moon, so the moon, new moon, the moon is between the Earth and the sun. I think that's what they're looking for. The moon is between the Earth and the sun. All right, and then this one. During the time of a full moon, okay, so let's go back to this picture. During a full moon, the Earth, see, here's the full moon. The Earth is between the moon and the sun. All right, so that's what they're looking for that one. All right, so during the time of a full moon, you see the Earth is between the moon and the sun. You just look at the picture. That's what they're asking about. What I was trying to answer the end of the last video was, from the Earth's perspective, what's going on during a full moon, what's going on during a new moon. That's not the way they were thinking about the question, nor were they thinking about the answer that way. All right, I mean they're both equivalent. It's just thinking about it in a different way. All right, let's see. The moon's the Earth's moon. The magnetic compass aligns with the magnetic field. Like a compass in a magnetic field, the moon aligns with the Earth's gravitational field. Oh yeah, that's absolutely true. I don't know why they're bringing. So the moon doesn't have an overall magnetic field. It has, so it's this is kind of a misleading picture. But this is absolutely true. Like if the there's a magnet, if there's a compass, a compass is just a magnet that can pivot. But if there's an external magnetic field, and the compass of course has its own magnetic field, the magnetic field of the compass will tend to align with the stronger magnetic field, the stronger external magnetic field, and so. So the same thing goes with the Earth and the Moon system. The Moon tries to align itself with the Earth's magnetic field, and that actually is the reason that when the Moon orbits the Earth, we always have the same side of the Moon that faces us. The Moon actually spins all the way around on its axis, but we can never actually see the far side of the moon, because it's kind of like a game of Ring Around the Rosie, right? You as you spin around, you like the back of your head never faces the inside of the ring. Anyhow. It's one of those demonstrations you actually have to see to understand. It works a little bit better. All right, but anyhow, there is the dark side of the moon and the side that we see. The dark side of the moon, or actually, it's a bad term using the dark side of the moon. The side of the opposite side of the moon does get light. It's just that we can't see that. Because of the way the moon orbits the Earth. It orbits in what's called synchronous rotation. The time it takes to orbit the Earth is exactly the time it takes to spin around its axis once. All right. So anyhow, an eclipse is when the moon shadow hits the Earth, and more than likely the moon shadow, of course, will hit the ocean, right? Because 71% of the Earth's surface is ocean. This is a much more common thing to see. Is what's called a lunar eclipse, right? This one, of course, a solar eclipse, a lunar eclipse. It just has to be dark when the moon passes through the Earth's shadow, right? And again, this doesn't happen all the time because the moon is actually tilted. It's tilted by about 5 degrees with respect to the Earth, and so usually the moon is up here or down here, and so it doesn't normally pass through the Earth's shadow. But when it does, you can see a lunar eclipse. And these lunar eclipses, by the way, are never the moon is never completely dark because the Earth's atmosphere, this thin little band that we need to live, is it acts like a lens, and so it'll bend the red light more than the blue light, and so the moon will look during a lunar eclipse, the moon will look definitely it'll be dark, but they'll have like a reddish tinge to it. They're showing that, and it's just because of the Earth's atmosphere. All right, so moving on from the moon, we'll talk about other objects in the solar system. There's asteroids. These asteroids are, again, the main asteroid belt is between Mars and Jupiter. I mentioned that before, so that's called the asteroid belt. But it's not the way it's depicted in Hollywood or any Hollywood movies or anything like that. Where if you were out in the asteroid belt and you saw an asteroid, you could look around and you'd not see the next asteroid over. It's really they're really spaced apart. There's a lot of room between Mars and Jupiter. There's a huge amount of room. So these things are not spaced together. Another misconception is that the asteroid belt, and there literally are thousands of these things out there between Mars and Jupiter. That's not the only place that we find them, but that's where most of them are. That is not a failed planet. Sometimes people think that's why they're there. They are there mostly because of the incredible mass of Jupiter. These rocky bodies end up there. They're mostly potato shaped. Some of them are big enough to be round. The largest one is called Ceres, and there's another one called Vesta and Pallas, which are about half the size of Ceres. We've actually sent spacecraft that have orbited Ceres and orbited Vesta, giving us lots and lots of information about them. We do find little chunks of these things on Earth sometimes. We find them, as it says here, in the Antarctic. It's easier to find them in the Antarctic because there's places where it's mostly white, this frozen area, and then there's all of a sudden this very dark rock there, and it doesn't really seem to belong. And so that some chunk of material has made it through the Earth's atmosphere and landed there. Most of the stuff lands in the ocean, but it's not like we have access to all of that. You can't just walk along and find it. Let's see. So comets are very different than asteroids. The best description of a comet is a dirty snowball. Oh, they even said that right here. Look at that. It's a dirty snowball. That's a very common description of it. You find a lot of the short period comets come from the Kuiper belt. Remember, that's beyond the orbit of Neptune. But there's another region that's even further than the Kuiper belt. Now, how far out this is, nobody's exactly sure. It's called the Oort cloud. Oort was a guy, I think he lived in the 1950s, and he proposed this region. And this is still just what's called this is completely theoretical. Nobody's actually seen the Oort cloud, although most scientists feel that it's almost certainly out there. And the reason is, let's see, if we have there's a nice picture. Here's a good picture of the sun. Okay, so here's the sun. Let's say that this. So I'm going to make a line that's parallel to this line right here that goes through the sun. All right, let's say that right along here is the path of the ecliptic, or that's where you find. Of course, they're drawing this a little bit differently. because where the Earth's orbit is. But anyhow, let's say you found most of the planets right along here, the path of the ecliptic. Then what happens? Of course, the comets come into the inner part of the solar system in all sorts of crazy angles. Like some of them can come in at 90 degrees with respect to the ecliptic, and these incredible angles. And the reason for that, and this is what Oort proposed, is that there's this spherical region around the solar system, that surrounds the solar system, which is part of the solar system. It's called the Oort cloud. And so this is a region of icy material, that's a proposed region where many of the comets come from, the long period comets come from. All right, so like the Kuiper Belt, for example, Halley's Comet, probably the most famous of all the comets, has an orbital period of about 70 years. So it takes it, out into the Kuiper Belt, but then it comes back, once every 70 years or so. The comets are highly elliptical orbits. So this is an example of an ellipse. They're showing you an example of what the planet is. Planets do travel in slightly elliptical orbits, but they're almost circular. This is a very extreme ellipse. All right, so it has high. It's highly elliptical. So let's say you have a comet coming in, and it gets closer and closer to the sun. So what happens is, since it's an icy snowball, as it gets closer to the sun, that ice begins to turns directly from a gas into a solid. That's called, it turns directly from a solid to a gas, the other way around. And that gas escapes off the comet, which, by the way, means that every time a comet passes by the sun, it loses part of itself, which is absolutely true, right? In a couple of million years, there won't be a Halley's Comet anymore, because, it'll have gone around the sun enough times that it loses itself, or it loses all of its material. Sometimes, and we've seen this happen, comets come in and they just simply crash right into the sun. So there's this region, again, around the solar system, around where the planets are and where the Kuiper Belt is, where these snowballs, these icy bodies exist. And most of them are just sitting out there, and they're orbiting the sun in these incredibly long period. That takes thousands upon thousands of years to go all the way around the sun. But occasionally these things will disturb each other, and one of them will head in towards the inner part of the solar system, and then when the gas and dust get sublimated, then that's what we see. We see this tail. And the tail, by the way, is always away from the sun. And in fact, most comets will show two different tails. One's called a dust tail, and one's called an ion tail. The ion tail will follow the sun's magnetic field. All right, so let's see. Asteroids are small rocky bodies. They're not all rocky, by the way. There are some metallic ones. There's some carbon ones as well. Anyhow, small rocky bodies that orbit the sun, may reside between Mars and Jupiter, are smaller. That's all of those are true. All right. The tail of comets point in a direction always away from the sun, and that's actually because of solar radiation pressure. The radiation from the sun actually will push the sublimated particles, the particles that are now gas, and that's what you see. Like when you look up and you see a comet's tail, it's that gaseous material that is very, very bright, and the sunlight is shining off of it, but it's always pointed away from the sun. Oh,